Okay, so in this video, I will be covering the concept of titrations and all related topics. I will also show how to perform some stoichiometric calculations to figure out the molarity of sodium hydroxide using a standardized solution. And then we'll figure out the milligram content of ascorbic acid in vitamin C tablets. Now, let's go ahead and get started with the concept of titrations first of all. Now, the word titration is defined as the process of adding one solution into another very slowly until the reaction has gone to completion. Okay? Now, in the case of our reaction today, we're going to obviously have an acid-base neutralization reaction. The acid obviously is going to contain the H plus ion with the aqueous symbol indicating that it's an acid and it's dissolved in water. And then it will be reacting with the OH minus ion in the base. And again, it will be an aqueous solution, meaning it's dissolved in water. The H plus ion is going to react with the OH minus ion to produce water, and then we will also generate some sort of salt depending on the identity of the acid and base. And this salt is most likely going to be in aqueous phase also. Now I'm going to go over the setup of titrations, how the entire experiment is set up, and then we'll go into more details. Now what we typically have is some sort of a stand holding the burette, okay? Now, if you guys remember from previous experiments, the burette is an inverted system. So we typically read it from the top to the bottom. Your lowest calibration mark is going to be at the top, so that the 0 mark is going to be at the top. And then your highest number or highest calibration mark is going to be at the bottom, which is going to be the 25 in the case of our particular burette. Now, keep in mind that we usually start taking measurements on the burette by recording the initial volume reading, and that's going to be the before we even start the titration, we're going to have to fill the burette up all the way to the top with sodium hydroxide. And that's going to be the initial volume reading we're going to be recording at the start of the experiment. Now, once we've finished the entire experiment and we've delivered the entire amount, the amount that's required to get the desired product, then we're going to record our final volume reading. And the difference between the two is going to be an important reading called the total volume delivered, which we're going to use in a lot of calculations. Now, I'm going to leave this at that, and I will come back to this concept later on when I go over the calculations. I will remind you that I got this number from this part of this setup, okay? Now, underneath the burette, we typically have an Erlenmeyer flask containing an acid. Now, keep in mind the acid will vary in different parts of the experiment. In the first part, the acid will be sulfuric acid. In the second part of the experiment, the acid will be ascorbic acid. This is why I'm just leaving it at the generic form. We're also going to have a small magnetic stirrer, which is going to be operated by the stirring mode on the hot plate, okay? Keep in mind the heat mode will be turned off because we obviously do not want any heat to affect our titration. So that's going to be off, and the stirring mode will be on to mix everything together, okay? Now, if you guys remember, in regards to acid-base neutralization reactions in the aqueous chemical reaction video, I told you that both acids and bases are clear and colorless. So both reactants are going to be clear and colorless, and the products are also going to be clear and colorless. And that obviously causes us some problems because we're not going to really be able to determine whether we formed the desired products or whether the reaction has gone to completion. Now, if you guys remember in that video, I told you we pretty much rely on two basic methods of observations. The first method is going to be the bubbling process. Remember, because acids and bases react violently with each other, they do bubble quite a bit when they're reacting. And once the bubbling stops, that's when they actually produce the products. Okay? The other method that I told you we rely on was the fact that the acid-base neutralization reactions do produce a lot of heat. They are exothermic reactions, so they do produce heat. So if you were to actually touch the reaction vessel or the test tube, you will actually feel that heat is being produced. But again, both the bubbling and the heat production are not very reliable in the case of titrations, because that's not going to actually tell us much about what's really happening at which point in the reaction. We want to know exactly when we're having an acid and when the neutralization happens and when the base becomes introduced into the solution. Okay. Now, let me move on to the graph. I will be going back and forth between the two, the graph and the diagram, between the two parts over here in explaining the concept of titration. Now, over here on this graph, on the y-axis, we have the pH scale ranging all the way from like 0 to 14. And on the x-axis, we have the volume of sodium hydroxide being delivered. Okay, that's what we have over here. Now keep in mind we're starting somewhere close to like the 0 mark. The reason for that is because when we start with the titration, all we have in the solution is just pure acid. We don't actually have any base whatsoever. It's just pure acid, and this is why we're starting somewhere around like a 1 or a 2, okay, a pH of 1 or a 2. Now keep in mind anywhere between like a 0 to like a 6.9, this is what we consider as the acidic range, okay? Now once we get to like that pH of 7, this is what we call as the neutral pH of only chemicals. Keep in mind this is not the neutral pH of a human body. Inside a human body, the pH is slightly higher than 7, okay? And you'll learn more about that in like higher physiology classes. So I just wanted to mention that because a lot of students think pH of 7 is inside a human body, and that's incorrect. It's only for chemicals. Okay, so that's our neutral pH. Now, anywhere above like 7, so like from like a 7.1 onwards until like 14, this is what we consider as our basic range. Okay, now remember when I told you that over here, when it's very unreliable of us to actually count on the bubbling and the heat production. This is why we actually end up using what we call as an indicator. The indicator is meant to be like a certain substance that we actually add to our reaction vessel, which will change colors in different mediums. So the indicator will have a certain color in an acidic medium, and it will have a different color in a basic medium, which makes it very ideal for figuring out whether we have an acid at a certain point and whether we have a base at another point, okay, or not. Now keep in mind there are many indicators. The one we're particularly using in this experiment is called phenolphthalein. Now phenolphthalein happens to be colorless in an acidic medium, and it happens to be a dark pink color in a basic medium, okay? Now, if we go back to our graph over here, we did say that anywhere from like a 0 to like a 6.9 is an acidic medium. So at this point, you technically should have the colorless color within the acidic range. Now, once we get to like the neutral range, this is when we're supposed to actually get that pale pink color. Now, I have a couple of comments about this pale pink color, but I will comment about that later. But for right now, just remember that a neutral pH is a pale pink color. Now, once we move on to like the basic range, this is when we're going to get the hot pink color or the dark pink color, and that's representative of the basic range, okay? Now, let's start from the beginning. We're starting over here with the acid, okay? We're adding, now we're increasing the amount of sodium hydroxide we're adding into the solution. So we're increasing the amount of sodium hydroxide being delivered. What we're going to notice over here in the solution is we're going to actually start seeing flashes of pink as soon as that sodium hydroxide is allowed to drip into the solution. So as soon as we start dripping it into the solution, we're going to actually start seeing flashes of pink. Now I'm going to indicate the flashes of pink with like little crosses over here. Now what we're going to see is the solution, the acidic solution will flash with a dark pink color and it will disappear. It will flash again with a dark pink color and it will disappear. And this will keep happening for quite a bit of time. It will happen for a couple of minutes. And as we keep approaching the neutral point, these flashes are going to become more intense and closer in intervals, okay, until we actually obviously reach that neutral pH, okay. Now, one thing I want to mention is why are we seeing those flashes of pink? Now, it's very understandable for us that at this point we are getting the colorless color because we're in the acidic range. But if we were to actually get these flashes of pink, we need to understand why that's happening. Now, if we go back to this diagram over here, I'm just enlarging this little Erlenmeyer flask so that we can see what happens inside of it. So we know there's acid, so I'm going to draw that. I'm going to draw a bunch of H pluses representing the acid that's present in solution. So we're going to have a lot of that in solution over here. Now, if this is like the tip of the burette over here, and we're dripping the sodium hydroxide into the solution, obviously, as soon as this droplet hits the solution, remember we do have the phenolphthalein in the solution. So as soon as that hydroxide ion hits the solution, this is when it's going to appear as a hot pink color, okay? So we're going to definitely see that hot pink color appearing locally only in this spot. And then because we have so much of the H plus ions in solution, what's going to happen, all of these H plus ions are going to dominate over that very tiny bit of hydroxide ion that's in solution. And as soon as the H plus ions dominate over that little local spot of pink, hot pink, they will dominate over it. One of the H pluses is going to react with the OH minus ion and it will immediately form water. So these two are going to combine and they're going to form water, but keep in mind the solution is not neutral now. It's only forming one molecule of liquid water, okay? So this is one instance of like the OH minus ion appearing in solution as the hot pink color, and as soon as it forms the water, that's when the color actually disappears. And this will keep happening over and over again. So we will see every time that droplet of the sodium hydroxide hits the solution, this is when we're going to actually see the hot pink color, and it will disappear as soon as one of the H plus ions forms the water. And then because there's a lot more of the H pluses in the solution, they will dominate over the solution and they will turn the solution back to a colorless solution, okay? So we will see that local pink color, and again, it will disappear immediately. Now, as I said, the whole flashing business happens quite a bit, and it will become intense until we're very close to the neutral pH. Now, once we reach that neutral pH, the entire solution is going to turn into a pale pink color or a baby pink color, okay? Now, here's my comment about the pale pink color. If you guys remember, we said that phenolphthalein is only going to turn pink in a basic medium. So whenever there's sodium hydroxide. So technically, once we reach the neutral pH, technically all of the H plus ions will have reacted with all of the OH minus ions, and the entire solution is predominantly going to be predominantly made of water, except for the fact that there's going to be one extra hydroxide ion in solution, which will register as a pale pink color. So technically speaking, when we get this pale pink color, we have one extra hydroxide ion in solution in addition to all of the waters that are in solution. Okay, so technically speaking, it should be basic, but because it's extremely hard for us to actually figure out the neutralization point in any other way, that one extra hydroxide ion is the closest we can actually get to neutralization point. And therefore, we consider the pale pink color as what we call as equivalence point. Okay, so this is what we call as equivalence point, and this is equal to the neutralization point. Okay, so this is equal to the neutralization point, and this is what we call as equivalence point, and equivalence point is a very important term over here. It means that we have equal amounts of the H plus concentration, which is equal to the hydroxide concentrations. So we have equal amounts of the H plus ion and the OH minus ion, and we do tend to ignore that one extra hydroxide ion that's present in this part of the reaction. Okay, now keep in mind that when we were having the flashing business happening and when we were still in the colorless phase, this is all when we have a lot more of the So this is when we actually have a lot more of the H plus ion. I'm going to erase the O because it shouldn't be there. This is when we actually have a lot more of the H plus ion, okay? And once we actually reach the basic range, once we actually get the hot pink color, this is when we actually have a lot of the hydroxide ions in solution. Okay, so over here we have a lot of H plus ion. When we get the pale pink color, we have equal amount of both. And then when we actually are in the hot pink range, we have a lot more of the OH minus ions. Okay, now there's one other important factor over here, one other important point. If we end up like adding one extra drop of the hydroxide ions into solution, okay, if we add one extra drop past the pale pink color, this is when we're actually going to get the dark pink color, okay? So we're going to get that hot pink color or the dark pink color, and this is what we call as end point, okay? This is what we call as end point. Now, end point, I want to emphasize that end point is not neutralization point. It's past neutralization point. So at this point, you are definitely having a lot more of the hydroxide ions compared to being neutral. You're definitely not neutral. You're definitely in the basic range, so you have a lot more of the hydroxide ions. Whereas equivalence point is exactly neutralization point, and it's where you have equal amounts of the H plus ions and the hydroxide ions. So please make that distinction very clear in your head. Endpoint and equivalence point are not the same thing. We technically are, if we want a successful titration, we technically should stop at equivalence point. That's where we actually get the pale pink color, and if it lasts for 1 minute, we know for sure that we have done a successful titration and we have reached the neutralization point. If we reach this dark pink color by adding one extra drop, we're definitely in the basic range and we have missed neutralization point. Okay, I hope this is clear in regards to this concept. Now, there's one more thing that I want to go over here, which is Sig Figs. You're obviously going to be recording a lot of numbers in this experiment. Now, if you remember from previous experiments, we did talk about the Sig Figs that deal with the burette. More specifically speaking, we did say to record 2 decimal places for a burette. Remember, the Sig Figs could vary. They could be 2, 3, or 4. if your value is somewhere between like a 0.00 to like a 0.99, that would be 2 sig figs. If you're like between a 1.00 to like a 9.99, that's 3 sig figs. And if you go from like a 10.00 to like a 25.00, that's like 4 sig figs. So the sig figs could vary. If you just watch out for the decimal places, you should be able to get the question, the reading done correctly, okay, or written correctly. Now, the other thing I want to mention in regards to the sig figs is in regards to the volumetric pipette. Now, the pipette is going to be used to deliver the acid into the Erlenmeyer flask. We are specifically being told that we are using a 10 ml pipette. Now, if you actually look at a pipette, there's only one calibration mark on the pipette, meaning this pipette can only carry or deliver 10 mils exactly. This is why it's going to be a very accurate reading. So it's going to be recorded as 10.00 milliliters. And keep in mind, we cannot record any other reading for a pipette other than 10.00 because again, we only have one calibration mark and we need to get the liquid up to that level exactly. Okay. Now, let's move on to talk about the calculations, okay? Now, over here with the calculations, in the first part of the experiment, what we're going to be doing is the standardization of a sodium hydroxide solution. Now, I kind of want to go over why are we doing this. When we're doing the standardization of sodium hydroxide, the reason why we're doing it instead of going directly to the ascorbic acid titration is because we actually do not have the molarity value for sodium hydroxide. It's extremely hard for us to determine the mass of sodium hydroxide in solution. This is why we actually have to go through another known solution to be able to calculate the molarity of sodium hydroxide. Now, some of you might be wondering, why are we even interested in sodium hydroxide? The reason for that is because we are going to be using sodium hydroxide to titrate the ascorbic acid. So we literally have to go through all of this work in order for us to determine the molarity, which is going to be used, the molarity of sodium hydroxide, which is going to be used in determining the milligram content of ascorbic acid. So this is the point of why we're doing this part of the experiment. Now, when we're reacting, since we're reacting in this part, the sodium hydroxide with sulfuric acid, again, everything's going to be acid-based today. So this is a base reacting with an acid. The first product is going to be immediately liquid water, okay? And the water is obviously coming from the H and the OH. And then the second product, which is going to be the salt, is going to be produced as sodium sulfate, okay? So sodium sulfate, obviously the sodium gets a subscript of a 2 because the sulfate has a charge of -2, and this does not, the sulfate does not get any parentheses or any subscript because the charge on the sodium is a +1, okay? Now, if you look this up on solubility rules, it should be aqueous. This is why I'm giving it an aqueous phase over here. Now, let's balance it real quickly so that we can start with the math. Over here we have 1 sodium atom, and over here we have 2 sodium atoms. So we're going to add a coefficient of a 2 over here for the sodium. Over here we have 1 sulfate ion, and we have 1 sulfate, so we're not going to touch that. And then for the H's and the O's, if we start with the H's, we have 2 hydrogens, and we have another 2, so that's a total of 4. And over here we only have 2, so we're going to add a coefficient of a 2 over here, which makes it 4. And then we have 2 oxygens and 2 oxygens, and that should balance your chemical equation. Now again, I want to remind you what we're looking for is the molarity of sodium hydroxide. Now, whenever you're starting any stoichiometric expression, you always start with the given information. Now, if you look up the information you're given in the handout and in the instructions video, you're going to be told that we're given information about about the sulfuric acid. So that's what we're going to start with. We're going to start with the milliliters of sulfuric acid. Now, if you guys remember, I just told you just like about a minute ago that in the pipette we will be measuring out 10.00 mils exactly, and that's what we're going to be using over here. That's where I'm getting the 10 from. Now, we need to do a simple conversion to go from like milliliters to liters. So we know that 1 liter is equal to 1,000 mils. The mils of sulfuric acid cancel with mils of sulfuric acid. By the way, I highly recommend that you include the units and the labelings of everything very clearly in every step. That way you see what cancels, how the units actually cancel. Now, once we reach this point, we now need to convert from liters to moles. Now, if you guys remember what these units stand for, if we have moles over liters, okay, so moles over liter is actually equal to capital M, which is molarity. Remember, molarity takes the capital M, little m is for moles, okay? So capital M molarity is equal to moles over liters, okay? Now, some of you might be wondering, where are we supposed to get this value from? Now, this value changes every semester, and this is a value you're going to have to look up in the instructions video that's on Canvas. They should be giving you this value. It's a value that was measured in lab during the experiment. So you're going to take that value and plug it over here in this spot. And if you're obviously not given any other information, and that would be obviously the case for today's experiment, it will always be per 1 liter of sulfuric acid, okay? So you just need to literally look up this number. Now the liters cancel of sulfuric acid, and now we're at moles of sulfuric acid. Now this step over here is what we call as the molar ratio. It's going from like the moles of sulfuric acid to the moles of sodium hydroxide. And we usually get that from the balanced chemical equation. This is why we actually had to balance the chemical equation in the first place. Okay, so we're literally going to be looking at the coefficients. We have 2 moles of sodium hydroxide for every 1 mole of sulfuric acid. So we have, I'm going to just plug those numbers in. So 2 moles of sodium hydroxide for every 1 mole of sulfuric acid. The moles of sulfuric acid cancel with moles of sulfuric acid, and now we are at the moles of sodium hydroxide. Now keep in mind, this is not where we're supposed to stop, okay? At this stage, we're going to get, after doing this calculation, we should get the moles of sodium hydroxide, okay? This is obviously going to be a number you're going to calculate from this calculation. Now, we're not done yet, because we still need the molarity. Molarity is what we're looking for. So we need to take this number and we need to actually plug it into the numerator over here. That's going to be the moles of sodium hydroxide. And now we actually have to look up the liters of sodium hydroxide. Now, please do not make the mistake of entering a 1 just like how I entered it over here. The reason why I entered it over here was because the molarity value was already given and it's per 1 liter. But over here it's different. We actually have to plug in a special number for liters. This is when you're actually going to have to go back to your titration, okay? And again, this will be given in the videos, the instruction videos. This is when you're actually going to go back to this part and do the subtraction of V final minus V initial to get the total volume delivered. So I'm just going to write over here, this is your total volume delivered, okay, from the burette, okay? So it's going to be the V final minus V initial. That's what you're actually going to plug into this spot over here. And again, this spot is from this particular calculation. Now, once you divide these two, you should be able to get your molarity value, and that's what you're going to plug over here. Now, keep in mind, we are doing the titration 3 times, okay, for 3 different trials, because we always have to account for errors that are happening in the experiment. So this is when we're going to actually have to calculate our average molarity. Now the average molarity is going to be just the average of all of these molarities. So you're going to take the trial 1 molarity plus trial 2 molarity plus the trial 3 molarity, and you're going to add those together and divide by 3 to get your average molarity. Now, I just want to emphasize, you're going to obviously have to do this full calculation for every single trial. So this first calculation is going to be for trial 1. You're going to have to do this entire calculation again for trial 2 and again for trial 3. Okay, and that's when you can average your molarities. Now, the last thing I have over here is obviously the percent error calculation. It's very important to calculate percent errors in titrations to see how accurate were your results. Now, technically speaking, we need to be at a 5% or less as far as the percent error goes. Percent error just says how bad were your results, pretty much. So if we have like around like a 5% or less, that means that we if your percent error is 5% or less, it means that you pretty much did the experiment very accurately, and you had a very low margin of error. Now, what we're going to plug into this formula over here is we have the absolute values and then the experimental value. Now, the experimental value is pretty much going to be your average molarity. So that's what you're going to plug in here, okay? Now, then you're going to subtract it. You're going to subtract your experimental value from the accepted value. Now, the accepted value is a value that we've already measured in lab, and this is a number I'm going to give you. This number is actually equal to 0.1998 molar. Now, keep in mind this value changes every semester. Just for the purposes of this semester, I will provide you with this number. So that's the number you can actually plug into this formula to be able to do the percent error calculation. By the way, in the instructions video, it tells you to email me in regards to this video. I'm already giving you the number right now, so you can just immediately use it without emailing me about it, okay? So you're going to take your experimental value, your average molarity, subtract it from accepted value, and then get the number, divide it by again, that same accepted value, and then times it by 100. Please pay attention to Sig Figs in every step, and especially over here. If you remember, I went over this in great depth at the beginning of the semester where I showed you how to do Sig Figs over here. If you have any questions about that, you can email me about it, but this is how you're gonna actually plug your numbers for percent error, okay? And don't forget to include a little sentence or two about percent error. Obviously, if your percent error happens to be in that 5% range or less, then you've done your experiment very accurately, and you should obviously talk about your average molarity being either close to this value or not. It technically should be close. This is why your percent error has to be lower than 5%. So make sure to comment about percent error in your conclusion and include a little something about the comparison between your average molarity and the accepted molarity. Now, one last comment over here is please do not use the M1V1 is equal to M2V2 instead of this calculation. This is called the dilution equation, and it's not supposed to be used for acid-base reactions. The reason for that is because this equation does not take into account the molar ratio, okay? It assumes that we have a 1-to-1 ratio, and that's incorrect. And again, this is not the correct calculation to be, this is not the correct formula to be used for acid-base neutralization reactions and for stoichiometry in general. Stoichiometry is obviously a lot more accurate. This equation is only going to be used for dilution type of calculations only, okay? So for dilutions and concentrations, and that's it. Okay, now one more thing. This is going to be the last part of the experiment. this is actually going to be the part that we're interested in, and that's determining the milligram content of ascorbic acid in vitamin C tablets. Now, keep in mind what we're doing over here is the same exact procedure. The only difference is we're going to take a tablet, a vitamin C tablet, and we're going to crush it up into a fine powder. Now, that fine powder is going to be dissolved in some water, and then that's when we're going to set up the same titration setup. We're going to have our sodium hydroxide over here, and obviously this is the vitamin C tablets dissolved in water. Now, the only reason why I'm mentioning this is because the results are going to be slightly different based off of what we have. Now, keep in mind the vitamin C tablet is not the pure acid by itself. Vitamin C tablets are made of ascorbic acid, which is the acid we're interested in, plus what we call as a binder material. Now, this binder material is what gets in the way. It's a type of substance that interacts with like the titration. So the way it interacts, it obviously interacts in many ways, and because you guys are not doing a formal lab report, I'm just going to skip on all of the other irrelevant interactions, but I'm just going to comment about equivalence point in regards to this binder material. Now, the binder material happens to actually give you a slightly different color at equivalence point. So instead of getting that pale pink color, you're actually going to get more of like a peachy type of color. So like a salmon shade, a peachy shade, which is very close to like the pale pink, but it's not quite the pale pink color. So keep that in mind when you're actually when you're trying to figure out your equivalence point. You're going to get more of this color rather than the pale pink color. Keep in mind also, once you go into like the basic range, the end point, and everything that's after that, again, the color will be slightly different. You will be able to see the hot pink color, but it's not going to be as bright as in the case of like sodium hydroxide with sulfuric acid. So just wanted to mention that. Also, we happen to be very strict about counting the minutes over here. If we get the peachy color for like 1 minute exactly, we just consider that as the equivalence point and we move on, because again, the binder material happens to interact a lot with the reaction, turning the reaction again acidic, which is obviously not the most ideal condition. Okay, so now I want to show you the calculation of what we're going to be doing. We're obviously starting with the ascorbic acid. Okay, we're only going to be considering the ascorbic acid in this calculation. Now keep in mind the the vitamin C tablets are actually set to be 500 milligrams in the tablet, and that's another thing I'm going to mention later on that you have to comment out on when you come to the conclusion based off of your findings at the very end of the calculations. So you're starting with the ascorbic acid, reacting with the sodium hydroxide. So that's an acid reacting with the base, producing liquid water, and then obviously the liquid water is coming from the H and the OH, and all we're left with is the sodium ascorbate. Okay, and that's what I get as the salt. Okay, now when we start the calculation, we're obviously looking for the milligram content of ascorbic acid. Remember, we're always starting with the known substance. The known substance is going to be the sodium hydroxide in this case, unlike obviously the previous case where the known was the sulfuric acid. Okay, we're flipping kind of the scenario over here. In the first part of the experiment, the sodium hydroxide molarity was unknown and the sulfuric acid was the known, but over here the known substance is going to be the sodium hydroxide, and that's why we're actually starting with that. Now we're going to start with the milliliters of sodium hydroxide. Now this is not going to be a given amount. This is going to be an amount that you have to read from your burette. So this is going to be again something you're going to be given in the instructions video. So you have to go back to that. This is going to be the total volume delivered of sodium hydroxide. So I'm just going to write total volume delivered from your burette. Okay, so final minus initial, in other words. So V final minus V initial is what you're going to plug in here. Now we need to convert from milliliters to liters again. 1 liter is equal to 1,000 mils. The mils cancel, and now you're at liters of sodium hydroxide. Now at this step over here, you're going to convert from liters to moles. Now again, if you recognize that, the units of moles per liter is molarity. Now this is going to be the value that you plug. This is going to be the value that you get from this particular calculation in the previous page. So remember, you had to actually figure out your average molarity. The average molarity value is very important. It's important for the percent error, but it's also more important for this particular calculation. So you're going to plug this number as your average molarity from part 1, okay? From part 1. This is what you're going to plug into this spot over here, okay? That's what you're going to plug in here. Obviously, this is per 1 liter, okay? So this is for part 1, and it's per 1 liter of sodium hydroxide, okay? Now, again, the liters of sodium hydroxide are going to cancel, and now we can actually use our molar ratio from the balanced chemical equation. We have, if we actually look at this equation, I skipped the balancing part because it is balanced. So we do have 1 mole of sodium hydroxide for every 1 mole of ascorbic acid. So we have a 1-to-1 molar ratio. The moles of sodium hydroxide also cancel with the moles of sodium hydroxide down here. And then what we need to do next is go from moles of the ascorbic acid to the grams of the ascorbic acid. Now, if you guys recognize this unit over here, grams per mole is what we call as molar mass, okay? Now, this is when you literally have to go to your periodic table and look up the formula of ascorbic acid. So you literally have to look up the H's, the carbons, the hydrogens and oxygens, and times them by the subscripts. Look up the mass, times it by the subscripts, and get your molar mass. And the molar mass is what you're going to plug over here in the top in the numerator. And again, it will be per 1 mole of ascorbic acid. And again, the moles cancel. And now over here you have the grams. We still need to take it one step further, which is going from grams to milligrams, okay? Now this is obviously a very simple conversion. 1 gram is equal to 1,000 milligrams. The grams again cancel with the grams of ascorbic acid. And now, after doing this very long calculation and including obviously timesing it at the very end with the 1,000, you're going to now get your milligram content of ascorbic acid. Now, keep in mind we're doing this entire titration twice, so we're doing 2 trials of this titration. So you are going to have to get your average milligram of ascorbic acid again. So you will take whatever you get at the very end over here from this particular calculation as your trial 1 milligram. And then you will do a second calculation for your second calculation for the second trial. And that's what you're going to plug in the second spot. You're going to add them together and divide by 2 to get your average milligram content of ascorbic acid. Now, the last step over here is going to be just getting your mass percent. Your mass percent is going to be is equal to the experimental value divided by the actual value times 100. Now, keep in mind your experimental value is this average milligram content of ascorbic acid. That's what you're going to plug for experimental value. Now, for the actual value, what you're going to plug over here is going to be the weighted amount at the beginning of the experiment. Remember, So this is the weighed milligrams at the beginning of the experiment, before you even did anything with that tablet. Remember, that tablet has to be weighed before even doing anything, just like any other experiment you've done in the past. So you're going to take that tablet, weigh it in the balance, and that's what you're going to plug for the actual value. Obviously, keep in mind the two units have to be the same. And then you're going to times it by 100, and you're going to get your mass percent. Now, obviously, the mass percent has to be close to 100, ideally. If you need to talk about your mass percent in your conclusion, whether you got something close to 100% or not. If you did not get something close to 100%, you need to elaborate why that's the case. Keep in mind, a lot of mistakes could happen in this experiment. You could literally miss the equivalence point. You could, spill some of the liquid. So talk about any errors that could happen over here. So you're going to mention the mass percent in your conclusion. Other things that I've mentioned, obviously, over here, that you need to talk about your percent error, and you need to talk about your average molarity in comparison to our accepted molarity, okay? And then you should be able to finish your lab reports. So I hope this video is helpful in regards to titrations and equivalence point and all of the concepts and the stoichiometry. If you guys have any questions, you can email me or let me know down below in the comments, and I will get back to you as soon as I can. And that should be it for titrations. I'll see you on the next video. Bye.